Hello, hello, listeners and learners. Today we are working on the chemistry in biology section, all part of our overall foundational molecules unit. I plan to go through this relatively quickly, mostly because I feel like in most bio classes, this is the unit that takes a long time, and most students have already had some amount of exposure to chemistry, and you really don't talk about the details of chemistry that are super relevant to the specifics of biology until you start talking about enzymes and redox reactions and electron transport chain and all of those very fun and exciting things. So we're going to go through this pretty quickly, but obviously if you have any sort of questions, please leave them in the comments. I will happily do my best to answer those. So moving right along. Matter. It matters. It's composed of atoms, and atoms themselves are composed of a nucleus, which has protons and neutrons, and this electron shell, or series of electron shells, or orbitals. Oftentimes, you will be looking at your chemical inside a periodic table. You have the chemical symbol here in the center, and then your atomic number. Your atomic number is the same as your number of protons, and that's characteristic of the element. So carbon is always going to have 6 protons. If it didn't have 6 protons, it wouldn't be carbon anymore. The thing that will change is going to be your mass. It's pretty small here, but the atomic mass you see on a periodic table, that is a weighted average. So the way that's calculated is taking into account the relative abundance of all the different isotopes, which we'll talk about in a second, and then calculating what the average weight of this element is. Elements are pure substances, and they consist of a single kind of atom. So in a sample of carbon, say, only going to be carbon. There's not going to be any other atoms in there. The atom is the smallest unit of your element. If you break apart an atom into subatomic particles, it no longer has the properties of that element. It just is those particles. But the properties of an element are determined by what that composition is. So that's made up of your number of protons. Like I was saying, that's characteristic of what your element is. Its mass. Different isotopes of an element have different numbers of neutrons. So that would be something like carbon-14 compared to carbon-12. So sometimes you'll see them written like this. So the 6 lets you know that that's the atomic number, and it's carbon, so that makes sense. But here you have 6 neutrons in addition to your protons, and here you have 8 neutrons in addition to your protons. So this is a slightly heavier isotope. Radioisotopes are unstable, so they can decay down to other isotopes. Depending on the type of decay, it'll either be losing neutrons or emitting gamma rays. Whatever the kind of radiation is will affect what it decays down into. Radioisotopes emit, for example, alpha particles. They can produce different elements. It's worth introducing the concept of radioisotopes, but because they're on a much larger scale than a typical biologic timescale, we aren't going to focus on them too much. The other piece, and the really important one when it comes to reactions, is your electron shells. So the way that your electrons are arranged around an atom is going to affect how they react with others. And basically, what's happening is your atoms are trying to seek a stable configuration, whatever that looks like for them. That is the driving force that is making those reactions happen. Our next vocab is compound. And a compound is another pure substance, much like an element. Compound consists of 2 or more elements that are bonded in a fixed ratio. So that means that H2O, water, it's always going to be 2 hydrogens, 1 oxygen, every single time. Table salt, sodium chloride, always going to be 1 sodium to 1 chlorine, every single time. That's what it means when it says fixed ratio. Next up, we talked a little bit about our bonds, right? Those are the things that make compounds and not just loose elements. We have a couple of different classes of bonds. So it's nice to think of them as strong and weak bonds when you're trying to get a feel for how they're going to affect how your substances are going to interact. In the case of covalent bonds, you have atoms that are sharing electrons within the molecule. The key word here is share. If you have a polar molecule, that means that they're sharing your electrons unequally. and your electrons are going to spend more time around the more electronegative atom, the one that's a little bit more loud and needy and really, really wants to hold on to those electrons. So it gets more time with the electrons overall. You can contrast that to a nonpolar molecule, which means that you have equal electron sharing. So the electron gets the same amount of time around each one of the atoms in your molecule. One way to keep this in mind is that a polar molecule pulls. Those sound kind of similar. It can be a little bit silly, but it also can be a really nice way to just keep them in your head. We're going to see a lot more about polar and nonpolar molecules. Next up is ionic bonds. So in the case of ionic compounds, your atoms are going to completely transfer your electrons. So when you completely transfer an electron, that means that one atom loses one, now your other one has one. When your atom loses an electron, it is now going to be more positive, which is a cation. The atom that gains an electron now has a negative charge, an anion. One thing I like to do to help keep cation and anion straight in my head is thinking of cats as very positive things, because people like cats, and anions are the other one. It's a little bit silly, but again, if it helps keep things in your head, it's worth remembering. So cats, positive, cations, positive. Worth noting, in the case of ionic bonds, is that they can undergo interactions with polar molecules that can help break apart those bonds more easily than if you, say, tried to heat them to break them apart. So salt, for example, would be really difficult to boil to loosen the bonds between it, but it dissolves readily in water. Next up, we're going to talk a little bit about a couple of the weak bonds. And just because they're weak does not mean they're not significant. They play huge roles in biology. So the strongest of your weak bonds are hydrogen bonds, which are between really strongly electronegative atoms and a hydrogen. Makes sense, that's in the name. Most of the time in bio, you're going to see that the electronegative atom is oxygen. Water is a covalently bonded molecule, which means that it's sharing electrons along its bonds, but it's polar, meaning it's an unequal sharing. Oxygen is a lot more electronegative than hydrogen is. The result, you sometimes will see the notation for the dipoles on your water molecules. So the way that is denoted is with a lowercase delta. Delta in pretty much any context just means change. Lowercase delta, little change. It's a little change in charge. It's not a full-on ion. It just means you have a little bit of a shift in charge because of that electronegativity difference. With your water, you have these negative dipoles on your oxygens, and you have positive dipoles on your hydrogens, which means that you can form hydrogen bonds between your hydrogens and oxygens on adjacent molecules. A good example of hydrogen bonds are on water, and we're going to talk a little bit more later about the importance of water in biology and how a lot of that comes from its ability to form those hydrogen bonds. Next, we have polar and nonpolar interactions. I said they were coming back. I'm not going to lie to y'all. So polar molecules are hydrophilic molecules. So hydro meaning water, philic meaning loving. Draw a little heart there so we can remember. As we just said, water is a polar molecule, so it would make sense that a other polar molecule would want to interact or seek to interact with other polar molecules. Similarly, nonpolar molecules are hydrophobic, so they are going to avoid water, they're going to avoid other polar molecules and seek other hydrophobic molecules because it's easier for those to interact with each other. This is mostly a vocabulary term. Oftentimes you'll see polar, hydrophilic used sort of interchangeably in a bio context, and this is why. Also of note, some molecules are amphipathic, which just means that they have both hydrophilic and hydrophobic regions. Water's really, really small, so it's just overall the whole thing is polar. But if you're looking at, say, a hydrocarbon that has a polar head, the end of that molecule would be polar, but the bulk of that chain would be nonpolar, which gives it some really interesting characteristics because it has both of those traits. Finally, in our world of weak chemical bonds, we have van der Waals forces. So van der Waals forces are temporary polar interactions. Even nonpolar molecules will have their troubles. Occasionally you'll have moments where they do form a little bit of a dipole and have some unequal sharing. When that happens, that temporary dipole can interact with other temporary dipoles within your sample when those two molecules are in close proximity. And granted, that single interaction is really weak. Compared to a hydrogen bond, very, very small. But if you have a very large molecule, it can undergo a lot of different van der Waals interactions with its neighbor. When you consider that additive effect, that can have a really substantial effect. One way that you see this is the change in boiling points, particularly when you're looking at hydrocarbons that have the same weight but different configurations. So I'm going to draw some sort of ugly hydrocarbon approximations. If you have hydrocarbon that's kind of globbed together, something that's bent together like this, there's only so many places where you can have interactions. But if I had a molecule with its exact same mass and the exact same polarity, but I stretched it out, so it has the same mass, but now it's stretched out instead of bunched together, it has way more spots where you can have those temporary dipoles and have those interactions. I'm going to go over chemical reactions and specifically acid-base reactions pretty generally, mostly because once we start talking about more specific examples in more detail, we can give them more of a biological context, and I think they're a little bit more meaningful. But just as a quick review, when we're looking at chemical reactions, we're talking about reactants moving to products. It's worth noting that some reactions are reversible and they can go in either direction. So in this case, my little arrow is going this way, showing you that it's going this direction, and these are the reactants and these are the products. But sometimes you'll see your reaction denoted like this, with either the top arrow or the small arrow a little bit bigger or smaller. And this is just saying that your reaction is reversible, so it can proceed in either direction. The big takeaway with chemical reactions is that matter is conserved. The amount of matter is going to stay the same. Things aren't just going to spontaneously appear or disappear. It all has to come from somewhere ultimately. Similarly, the way that energy works, and I'm gonna highlight this just because it is so significant. Your energy is your capacity to do work, and like matter, it's conserved. It is such an important concept. So a lot of biology, and we get into a lot of detail with this in the respiration and photosynthesis unit, is changing your form of energy so that it can be the most useful. So the way that energy is changing form and the forms that it takes is a really big part of bio, the movement of energy through systems. Finally, I'm going to breeze through a little bit of acid-base chem. You can think of acids and bases a lot of different ways, and the definition you're using for an intro-level bio course, it's not too precise, generally speaking. It's useful to think of acids as proton donors and bases as proton acceptors. This is technically the Bronsted-Lowry definition, but you can think of acids as substances that, when introduced to a solution, increase the concentration of protons, or H+, and bases as things that, when introduced to a solution, decrease the concentration of H+ of protons. I'd like to make the distinction between a strong acid or base and a weak acid or base. It doesn't have anything to do with molarity. A strong acid or base is something that fully ionizes in solution. So for example, a strong acid, like HCl, when you dissolve that in water, you're going to have H+, and you're going to have Cl-. You're going to have hydrogen ions, and you're going to have chloride ions. You're not going to have any of these whole HCl's floating around. It fully ionizes in your solution. Contrast that with a weak acid or base. You're only going to have that partial dissociation. So there is some reversibility, and you will still see some amount of that neutral molecule in your solution. Buffers are made up of a weak acid-base pair. And because the reaction that produces the acid-base pair is reversible, your buffer is able to minimize the effect of an added acid or base by accepting or donating protons as needed. The way we measure acidity or basicity is using the pH scale, using the concentration of H+. When you see brackets around something, That just means concentration of that substance. So in this case, we're talking about H plus, or protons, brackets, concentration of H plus. So this is our formula for pH. It's going to be the negative log of your concentration of hydrogen ions. The scale goes from 0 to 14. 7 is neutral. You may notice that 14 is a pretty small range all told, and there's a lot of variation in the acidity of things. And I think it's worth remembering that the pH scale is a logarithmic scale. And so a change in 1 on the pH scale is a tenfold change in acidity. So the difference between something that has a pH 7 and a pH 8, it's 10 times more basic, right? If you go from something that is 7 to 8, that's 10 times more basic. So just in terms of having a context and framing it in your mind, it's important to remember that it is a logarithmic scale. Finally, just wanted to touch back to the whole bio part of this, the reason we're talking about it. It's really important for biological systems to maintain this consistent pH. Enzymes only function at a certain pH. In general, the durability of your cell is based on that. For the organism to survive, you need to maintain a consistent internal environment, and part of that is the pH. So there's a lot of things that can be done, but the big one is using buffers. And buffers, like mentioned, are just a weak acid-base pair that can undergo that reversible reaction to buffer, to minimize the effect of any sort of added acid or base. For example, dissolved CO2 is going to pull down your pH, making your solution more acidic. So it's important, CO2, it's in your blood naturally. Your body needs to be able to have that buffering system, as it does, so that you don't wind up skewing your pH too much overall. So, super quick rundown of the basics of chem as pertains to bio. Please let me know if you have any questions. This is a very quick general review, but hopefully can serve as an effective primer as we move forward into some of the more complex reactions that an organism undergoes. Thank you for listening, and until next time, keep on learning.